Hello, everyone, and welcome back. I hope you enjoyed your lunch. We're running just 5 minutes late, so we're going to try and keep things ticking along. Now, this next section has been organized by Advenit Makaya, Aidan Cowley, and Alexandre Maurice. Alexandra and Aidan are on stage with me, and they will be organizing the questions that come in if we have time for questions. So please welcome our first speaker, who is Christiane Bergemann from OHB System AG, who will talk about the Commercial Lunar Surface Access Service. LSAS, do come to the stage, Service for Innovating Future Lunar Exploration. Thank you.
So, thank you very much. Presentation? Okay, thank you very much. So, I would like to present today a Lunar Surface Assessment Service that is an initiative from OHB, and we are here offering flight opportunities, short flight opportunities for any stakeholder that would like to bring a payload to the moon, no matter which are the motivation behind that. So, that I can go here with the next. Yes. So, why fly with us? So, LSAS is the only planet service worldwide with actual flight heritage. We are based here on the lunar lander, Bergemann. And we are here making, LSAS is exactly an upgrade for the Bergemann. The Bergemann was a small lander carrying 25 kilos payloads. LSAS is a little bit bigger and has a bigger payload capacity. And we are here bring the moon closer to everyone. That means offering short-term flight opportunities to surface on the moon. Like I said before, it doesn't matter the motivation behind that. We are here open and working together and cooperated with all kinds of payloads, institutionals, commercials. We are here open to everyone and also making co-engineering and help them to make it possible. So the partnership, or let's say the background and the heritage from LSAS is based in a very strong partnership between OHB and IAI. IAI is in Israel, in this Israel company, and it was the company that designed and developed the Bergemann activities. So in 2018, started these cooperations and the discussions between the both companies. In 2019, we signed a teaming agreement with them, and in 2020 we made a proposal to the open call from ISRU for the commercial partnerships. We have been selected, and we started a pilot phase that we just concluded now, and we signed this MOU starting like I said before, starting the pilot phase. So we are here a European mission. This mission is rooted in Europe. Also, if we have subcontractors in America and in Israel, but the biggest amount of subcontractors and, let's say investors and people that are interested in these activities are in Europe. Let's go to the next one. So here's a little bit how it looks like our system. So like I said before, LSAS is an upgrade from Bergemann. We have here a bigger capacity from 25 kilos from Bergemann. We passed to 85 and 110. The range there is because we analyze different options for launch scenarios. So if we go to a GTO launch scenario, we can carry a little bit less of payloads because we will need more fuel to move to the GTO orbit, to the moon orbit. And if we go with a launch scenario for TLE, translunar injection, we can carry a little bit more, 110 kilos, because we're going to be injected directly in the moon orbit. Our destination is the moon south pole. Why moon south pole? So there is different motivations behind it. I will show in the next slide some of them. Nevertheless, we would like to have the first ones in Europe to land in the moon south pole. So this is one of the motivations behind. Of course, there is a lot of science motivation behind that I will explain in the next slide. And here we would like to have, or we plan to have, at least 3 flights within this decade, one in 2025, one in 2027, and one in 2029. So the moon south pole. So that it's a very rich region, and the first motivation of this choose, it was based on a long-lived missions. We have discussions with different customers, and we realized that there is a need and a request to have long-lived missions to be able to collect data for more time. So we will have here at least a 2 months mission that it's not normal for this is a small lander. And it's also a region that it's very rich in a lot of kind of experiments. Since LSAS is a commercial mission, we don't have here a direct science there. We are open to all kind of science, and this is also a way to fulfill the requests and the requirements for the different customers, because we have there, like I said before, a very rich regions where we have also the PSR zones, very rich in volatiles. So with a small rover, we could be able to move also to these zones and also to make some experiments there. And this was, let's say, the reason behind that. And we here identified already an area where we would like to lander, and this is going to be in the Shackleton area. And yeah, and we studied together with the French company that make this assessment for us. And yeah, and this is the reason behind why we choose this area. So your payload on board, so that is a commercial mission. As a commercial mission, of course, that is also based in a price to fly the payload. So we have the first launch day in 2025, as I showed in the slides before, a payload capacity for 85 until 110 kilos. And here also we have some baseline for payload power and data rate, but this is, I should say that it's really a baseline. So the idea here is to make it possible to everybody, so that we work it together with the teams, with the payloads teams, with the customers to make it possible. And even if a payload will not fulfill these requirements or this baseline that we are writing here and they're presenting here, that it's not a blocking point to say we are not able to fly your payload. Of course, this is going to be request an engineering, co-engineering activities and engineering work, but we try really to fulfill the requests of all and the needs for all customers. Tailored price is also something different here, because we are used here of the American commercial activities and commercial service that are based in a kilogram price. Here we are not just based a kilogram price. We have a very unique price system. We are based a kilogram price, but we have add-ons. That means a static payload will not pay the same that's going to pay a dynamic payload that will pay. We need power and we need a lot of data rate to transfer data from the moon to the Earth. So we are here really working together and analyzing. Once we receive the technical requests from the customers, we make this price analysis and we discuss it with them, the final price and how we can fit how this cooperation can be done and how will be the future steps for this cooperation. So opportunities available to everyone. As I said before, we are here open to all the stakeholders that would like to go to the moon. So science, technical demonstrations, education, marketing, whatever. So just if you have this motivation behind and your, let's say, inspiration to come to the moon. So like I said before, we work together and we make it possible. So why LSAS? How LSAS came and how was the motivation behind it? So we made an assessment for some years ago, and we realized there is a gap there in Europe for activity, or for customers and for payload, not for customers, for payloads on the moon. So we saw that the next mission from ESA, it's going to be the L3, that's going to be, it's now planned for 2030, 2029, 2030 is the next plan for that. And we see that until now, until there is no presence, European presence on the moon. And we would like with LSAS, with this smaller lander than L3, much smaller than L3, so try to fill this gap and increase Europe stakeholders, increase the competitiveness of European stakeholders in the global exploration scenario. So, market opportunity for European companies. Here's a little bit to explain the motivation that a company could have when they decide to fly with us. So increase the TRL, increase the competitiveness in the market, in the space market. And some companies are not in this area, so they would like to accelerate the entry in the lunar market, and or they would like to position themselves for future competitions, for future proposals, for future activities. So, like I said, the motivation behind does not matter. What is important is that we can make it happen. So here's a little bit about the current status of the activities. Like I said before, we started this cooperation with ESA. We kick off in 2020. So we have here a decision point in the next ministerial. Why in the next ministerial? Because we are in contact with the member states and with the different delegations, and we are lobbying for these activities. We have a lot of interests from the member states and also outside the member states. So, but this is the point where the delegates will decide how the activities and the exploration will proceed, and so for us it's a key point decision for our commercial service. And like I said before, we cooperated with ESA. We just closed the pilot phase, and ESA is intending to be our first customer for these activities. We are still also under negotiation and discussions with ESA, but until now, the current situation shows that the way forward will be like that ESA may cooperate with us as a customer. So I think that is my last slide. Thank you very much.
Thank you so much, Christiane. We're going to try to keep to time, so unfortunately there's no time for questions live here, but of course, as always, you can direct the questions on the forum, on the chat, online, and I'm sure you'll be able to answer them there. Thank you.
Thank you very much.
So our next speaker is from Air Liquide. It's Pascal Barbier, Regenerative Fuel Cell Systems for Energy Storage on the Moon. Welcome, Pascal.
Is it coming? Okay, that's perfect. So good afternoon, everyone. So I will present to you an alternative to battery, a technology that could be an alternative to batteries called Regenerative Fuel Cell System. And this presentation has been made with our colleague from Clara that couldn't be present today. So first of all, a brief presentation of Air Liquide. So Air Liquide, this is a worldwide company that you might know for the big trucks that you can see on the road. But we are addressing different markets based on molecules and especially space, on which we've been involved for the last 60 years, especially through the Ariane program. And now we are targeting this new domain of space exploration, and especially ISRU and the energy. For Clara, this is a Norwegian-based company, mainly focused on research and development on advanced materials, on new space, on clean energy systems, circular economy, and biochemistry. There are around 70 employees, and they are really one of the most famous companies on RFCS, since they are working on it for now 20 years, around 20 years. So what is an RFCS, a regenerative fuel cell system? So this is a rather simple technology on which we will use hydrogen and oxygen as a storage media. So the idea is that when we have an excess of energy, we will split the water molecule into hydrogen and oxygen, store it. And when we need energy, we use that hydrogen and oxygen through a fuel cell to generate electricity and thermal power. So this could be really interesting in some specific use cases, like the moon, compared to batteries. So let's see at the main characteristic of RFCS. So first of all, the round-trip efficiency is around 60%, which is lower than batteries that could reach 90%. But on the opposite, the specific energy is higher at 400 watt-hour per kilogram, especially for the moon case, which is twice the value that could be reached currently by the state-of-the-art of batteries. Also, it can deliver constant power and has a high stability with respect to temperature. So for instance, if we take an example of the small lander going to the moon that needs 500 watts of electrical power during the lunar night, a battery system will weigh 800 kilograms. An RFCS will weigh around 400 kilograms, 400 kilogram of mass saving. So as I mentioned, it cannot be deployed in any use case, in any cases. For instance, on ESS, that's better to use batteries instead of LSAS. But on the moon, this system could be really a good alternative to save mass. So I will present some results that we recently get from an ESA contract on which we are working with Airbus, Clara, and Air Liquide all together. So this contract aims at realizing a breadboard, a TRF4 breadboard of RFCS, also a very detailed and versatile model. And the idea is to demonstrate the operation of the RFCS during 3 lunar nights, and also to be able to assess the capacity to reach the specific energy of 400 watt-hour per kilogram. So what we've learned from the model is that that this system is really, the mass of the system is made by the tanks and the molecules. So around 2/3 of the mass of the system. So if we want to improve the mass of the system, we need to focus on the tanks and the molecules. But not only. In fact, all the auxiliary equipment and the main equipments are interesting to focus on, and especially the fuel cell. For instance, if you lose 1% of efficiency on the fuel cell, you increase by 3% the mass of the RFCS. So that's really interesting also to improve all the different systems. So now let's have a look at the main component of the system. So first of all, the electrolyzer. The electrolyzer has been made by Clara. This is a high-pressure electrolyzer capable of delivering more than around 100 bars of hydrogen and oxygen, which is quite interesting because most of the electrolyzers are delivering 30 bars of hydrogen and oxygen. The fuel cell has been made by Air Liquide based on our ground components. So this is compatible with Puro 2 and with a high efficiency, around 55%. And for the storage, so this is really far away from a cutting-edge technology. This is COTS components, big bottles, but we hope that for the next contracts, we will have the opportunity to implement some new specific tanks to improve the design. So now the results. The results that we get. Currently, we are running the test. As you can see on the left-hand side of this screen, you can see the RFCS itself. So this is this cylinder. Only the tanks and the electronics are not present in this picture, but any other equipments are inside this cylinder. And so we are currently running the test with 3 cycles. The first 2 cycles are dedicated to simulating the lunar environment, lunar nights and day. And the third cycle, during the third cycle, we will simulate on-off behavior of fuel cell and electrolyzer to validate that it can sustain this transient phenomena. For the moment, we are at the end of the cycle 1. We monitor the fuel cell, so you can see the temperature inside the fuel cell, which is rather stable, which demonstrates that the fuel cell has a good health. And also, we monitor the polarization curves of the different cells of the fuel cell. So for the moment, everything happens well. We are at the first cycle. Let's wait for the third cycle. So the test should be running for the next weeks. And after that, we can imagine to improve, to mature the system, reaching TRL5 in 2024, then TRL6 in 2026. And then at that stage, we can imagine having a demonstration mission on the moon, to validate the technology, to de-risk the technology, and to prove that it can be a good alternative to batteries. But in the short term, what we have to do is to continue improvement and maturation of the fuel cell and the electrolyzer, develop an dedicated electronic with robust algorithm to be capable of autonomously drive the RFCS, mature all the auxiliary equipments, the pumps, the valves, the sensors, optimize the storage, and also optimize the design. And that's the end of my presentation. Do not hesitate to contact me if you have any questions. Thanks so much.
Thank you very much, Pascal. Fantastic timing as well. We might have one question.
Yes, one question, Pascal. Thank you for the presentation. From Thorsten online, he asked, how do you see the future of this concept as a long-term storage system for weeks or months?
On Earth.
On Earth. Okay, so on Earth, that's quite different because the cycles between day and night are not as long as for the Moon. So this is, I would say, different. And also on Earth, we have not this constraint of mass. So it could be an alternative if we look at the domain that requires low mass, aviation, for instance. So it could have an opportunity there. But let's be honest, for really ground application, batteries are mature, are really low cost, and can provide out of a good round-trip efficiency. So for the moment, there is no big opportunity on Earth, but let's wait and see what could happen.
Thank you.
Thank you very much, Pascal. Thank you. Our next speaker is also on site. It's Sebastian Rohde from the Institute for Chemistry and Technology of Materials with a talk entitled Robust Fuel Cells and Electrolyzers for Lunar Energy Systems.
All right. Okay. Thank you very much, and good afternoon, everyone. I'll just start a timer that I don't need way too long. Yeah, I'm happy to continue about the fuel cell and electrolyzer topic, as it was just introduced by Pascal Barbier. And yeah, this is my PhD topic. I just started 9 months ago, and I focus on the creation of robust fuel cells and electrolyzers, yeah, to have a secure energy storage and supply system on the Moon. This is a cooperation between my university and also the European Space Agency under the supervision from Aiden. And so next slide. Does it work? All right. Okay, so of course you can, as it was just explained, use fuel cells and electrolyzers to store energy by using excess electricity and, of course, talking about space resources, using lunar water. To split that water, as it was just explained, to get hydrogen and oxygen, and then as soon as you need the electricity, turn it back to water in the fuel cell. And I've tried to schematically depict how these systems look like. Fuel cell and electrolyzer are very similar systems from an electrochemical point of view. They both consist of an anode, a cathode, and in between there's a membrane. And note that as well, so if you talk about polymer electrolyte membranes and fuel cells, which have a very compact design, a high power density, so low weight, then the electrolyzer has a platinum cathode, and the fuel cell both has a platinum catalyst anode and platinum catalyst cathode. And this is important because, in the next slide, if it does work, yeah. So if you use lunar water, our best guess so far is from the LCROSS experiment, that it's, of course, not in a highly pure form, but unfortunately is probably very contaminated. So you can see you have a very high amount of sulfur, hydrogen sulfide, and also all other compounds, and they are all very problematic for your electrolyzer and your fuel cell system. So if you buy a hydrogen vehicle today and fuel it with hydrogen, then the total contamination level in that hydrogen must be below 300 parts per million. And in particular, sulfur compounds are of a big concern, so they need to be below 0.004 parts per million. And this is because sulfur is a very strong platinum catalyst poison. And since we use platinum in the electrolyzer and the fuel cell, this is not very good. And yeah, and the big thing is you might as well just purify the lunar water, but to get to these purification levels, you need a lot of energy. And then if you need more energy to purify your water, then it might as well doesn't make sense to use it as an energy storage and supply system. So how do we increase the robustness of such systems? We might as well just replace platinum. However, that's not as easy as that, since platinum is more or less the best electrocatalyst which you can get for this application. And so I've had a look into how do we produce fuel cells and also electrolyzers, since they're very similar. And conventional ones are made by just spraying or coating this catalyst layer onto the membrane, as you can see here on this graphic. And this leads to some platinum particles which are inaccessible to the reactants since they're just stuck within the matrix. So I've had a look at a novel method. It's called electrospinning. It's a method which produces nanofibers. I won't go into too much detail with this method, but you can get fibers which are in the range of 200 to 300 nanometers. And you create a catalyst ink slurry, pump it through a syringe, and apply high voltage. And then you can see here in my not so beautiful drawing that these fibers get pulled towards the collector and the diameter decreases ever more. And then there's a picture of my experimental setup, and you can collect some sort of fiber mesh at this rotating cylinder. And if we now look at it in the electron microscope, so in the left picture you can see freshly collected platinum electrode fiber mesh on the aluminum foil, and in the right picture you can see the same fiber mesh pressed onto the membrane, so you can see even if it's then transferred onto the membrane, it retains this fiber structure, and of course it's obvious that these have a way higher surface area, and hence there's more platinum available to the reactants, and it's therefore a more robust system since you can afford to lose more since there is more available. So just to give you some numbers, it's with a conventional coating method, I looked at a slot die coating process, you get a performance of like 1 watt per milligram of platinum, and with the electrospinning process you get roughly 5 times that. All right, so I think I'm very quick actually. So the main takeaway basically from this is that in some way or another we need to address lunar water contamination if we want to use fuel cells and electrolyzers. And of course we need purification. It might just be too costly to do that. So it's useful also to look into more robust fuel cell systems. With this method I had a look at, I think we can already have a right step in the right direction. It doesn't fundamentally solve the problem, but you have a more robust system and you have more freedom to play. Of course, as an outlook, so I just started 9 months ago, I'm trying to now not just improve the method, I'm also trying to improve the materials. So use some improved catalysts. But this is beyond the scope right now. And then in the end, I'll hopefully have like a super fuel cell, which is capable of dealing with all the contaminants, and I'll make a very toxic lunar cocktail and put that into a fuel cell system and see how long my fuel cell survives, and hopefully that's longer than a commercial one. And yeah, with that, I want to conclude. Thank you very much. Are there any questions?
Thank you, Sebastian. Yes, I have a question for you. I may have misinformation, but when you have your slurry and with your platinum particles, what's the matrix? What's the material where your particles are in?
Can go back. So you
Can we get back the presentation?
Whatever. So the matrix is, so you don't have pure platinum particles. You have platinum on a carbon support. And then I mix in some polymer, which is like actually kind of a glue, which makes it very sticky, so that you have these nice fibers. And then you disperse it in isopropanol and water, and you also add the ionomer naphthalene, which you need to have a proton conductivity. And this was actually the hardest part. So a couple of months I was just trying to get the amounts of the ingredients right, that you have actually a spinnable polymer, spinnable solution. And yeah. This is basically it.
Thank you for the recipe. Yeah.
Thank you. Are there any questions from the audience? A quick one. One quick question here from Jerry Sanders.
From Jerry, yeah.
But we need a microphone to race to Jerry, please. Is there a microphone around? Yes.
Consider alkaline or solid oxide electrolyzers instead, because those are much more tolerant.
Yes, of course. So this is also like my
Sebastian, if you could just repeat what
So the question was, had you considered alkaline or solid oxide electrolyzers, since they're much more tolerant to contaminants?
Exactly, yeah. So they are inherently much more tolerant systems. So the reason why I'm doing this right now is because how the funding for my project came together and from my university. But also polymer electrolyte fuel cells are they have a rather high technological readiness level. They are very compact systems because they have such high power densities. And
I would make sure that your research continues to compare those.
Yeah.
Because again, talking to my colleagues, robustness may outweigh mass in the end.
Exactly, yeah. Yeah, we're looking, so I'm definitely looking at those. The research group in my university works with PEM fuel cells, and that's how I ended up here. And we do not have a high temperature fuel cell test stand. I'm in the talks about that with my professor, but so far I'm working with those.
Okay.
Thank you so much. I wish we had more time for audience interaction, but we've got some great talks, so we're going to keep going. On site again, we've got Carmen Camañes from AVS Added Value Solution, and she will talk about the problem of ISRU reactor chamber sealing in lunar environments, an approach to the solution and how to test it.
Okay, hello everyone. It's very nice to be here. Thank you for your time. As you can see, my name is Carmen Camañes. I'm here to explain you one of the latest projects we had at ABS. It was a project to develop a sealing solution for a potential future ISRU process for oxygen production on the moon. Okay, we developed this activity under an ESA contract together with Open University and Airbus. So I'm sure that all of you know that that is a problem. We have known this since the first missions to the moon, the Apollo missions. In fact, I put a picture of one of the sample return containers, as according to the literature, all of the containers that came back to the Earth leak in the travel back to Earth. So we know that the sealing on the moon is extremely hard due to the dust. And that's a problem for any future ISRU oxygen production reactor, because as you may understand easily, if we need to put lunar regolith inside the reactor, we need some kind of hatch, and that hatch will need a seal in order to avoid the gas to escape from the reactor. No? So, for our activity, we identified the most, interesting oxygen production processes that are currently being studied. And from that point, we tried to find which was the most relevant parameter in order to select the seal. So we know that ISRU processes are meant to reduce the dependability from Earth. In that way, we need to achieve a sustainable oxygen production, and that means minimizing loss of both consumables and products, in this case, oxygen. But it's also applicable to any other ISRU process. And that leads us to the leak rate, which is one of the most critical parameters when we are talking about seals. So because of that, at the beginning of the project, we defined a maximum leak rate for brick event. This is the leak rate we will need to achieve, the maximum leak rate we might achieve in order to have a sustainable production, okay? As you can see, there are some numbers for the different processes. We analyzed this together with the Open University. This leak rate is different for all the different processes due to their different characteristics. I don't want to go into the details now, but you can approach me and ask me about this if you're interested. So, taking into account that leak rate, we defined some selection criteria, and based on that, we defined 3 different concepts that we would like to test and evaluate the performance. The first one is the melted gas knife. The second one is the restorable gasket knife edge, and the third one is the heated knife edge. I think the first and the third are pretty much self-explained by the drawing, and the second one, the restorable gasket knife edge, is a little bit complex. The idea is to melt the gasket when it is in open state. So the surface is even again after the closing. The idea behind all of this is that we need a seal that is reusable, which is also an important parameter for any potential reactor sealing. So once we had the concepts, we needed to manufacture and test them. And the test is quite an important part of the activity because it's a very complex assembly. We need to simulate the process parameters. We need to simulate also vacuum around and so. So we defined the test campaign for different processes, oxygen producing processes, with some dust amount based on the kind of amount of dust we will find on the lunar surface. And we tested the 3 concepts, different repetitions, 10 cycles for each repetition, so we have enough data. On the right side of the slide, you have 2 pictures of the breadboard we developed, one in open state and one in closed. This breadboard is like a mock-up reactor chamber. Okay, we have a very small internal area. We have the seal around and the preloading mechanism and so. And here you have a diagram of all the rest of the test setup we needed. Because this breadboard was meant to be pressurized with helium, we put this breadboard mock-up chamber inside a bigger vacuum chamber, make vacuum around, and then measure the leak with an helium leak detector. Okay? Here you have the picture of the actual setup we had, which is pretty complex to test only one seal, one small seal. And there's also an additional challenge on the test, and it's to achieve a repeatable dust deposition. For that, we developed a specific device, the dust deposition device. And here you have some pictures of the actual hardware we manufacture, and one picture that shows how it's assembled with the gasket in order to distribute the dust around the gasket in a repeatable and, well, relevant manner. And, well, the conclusions of the activity, which is the most important part, of course. It's clear that this application is really challenging. The solutions for the vacuum industry in Earth cannot be applied straightforward. For the activity itself, the tests are ongoing at this moment, but so far we have found that we are compliant with the minimum leak rate, the leak rate break-even that we defined at the beginning of the activity, so that's good news. We need to keep continuing with the tests and perform further tests to confirm the sustainability of this process for a higher number of cycles. So far, the restorable gasket seems the most promising concepts. And in summary, what I can say is that more work is needed for that. We think it's a key technology that we need to develop in order to be able to be on the moon and perform all those processes we are talking about in this conference. So that's all. We need to continue on this. Thank you so much for your time. If you have any...
Yeah.
Yes, thank you for the talk. Very interesting. I really like your dust deposition device. Maybe during your testing campaign, are you going to be testing at extremes of dust deposition? Are you going to be putting a lot of dust into the gasket? Or is it just like a faint trickle of dust?
We think that the dust is one of the main parameters. In fact, the early tests we have done so far have already shown that. We decided to go for a quantity of dust that is representative of what we could be dust in suspension on the lunar surface. Because if we go too far on one side or the other, if we go with too much dust, we will end up having results that show that we are not compatible with that, but that won't be realistic at all. So that's why we have finally decided for a medium, medium quantity of dust.
Okay. Look forward to seeing the results. Thank you.
Thank you.
Thank you, Carmen. There's another question for you online from Dan and Krull, which I'm sure you'll be able to answer. We do have to move on. Our next talk is online. Is Achim Seidel, who is from Airbus Defense and Space. Can you hear me, Achim? Hoping you're there, Achim. Have we got Achim? If I could have a thumbs up or not. He's connected, but he's not answering. Achim, can you hear me? I'll give it one more go and then we'll move on to the next talk. Achim, can you hear me? Achim, you're connected and you're going to do a talk on the metals factory on the moon, MEFAM. Can you hear us, Achim? Okay, we'll try to come back to Achim. On site, I'm going to throw you into it a little bit. Thank you very much. Sebastian Martin is next from the European Space Operations Centre, and you're going to talk about emission data systems for lunar surface operations. Thank you for stepping into the breach. Thank you.
Thank you. Thank you. Hello. So good afternoon. My name is Sebastian Martin. I'm from the European Space Operations Centre, so the center where in ESA we operate most of ESA's missions. And so our focus is really on the operation aspects. Operations will have an impact on your mission design. Operations will have an impact probably on your asset design. So this is what we are really interested in. Me personally, I'm a data systems manager. As data systems managers, we are responsible for the data systems that our flight control teams use and need to successfully operate their missions. So this includes mission control systems, simulators, planning systems, and other tools. And since this is my first time at the Space Resources Week, I want to give a quick overview of some of the activities that we are doing to prepare data systems for future lunar operations. We have heard a couple of times about a CDF, Concurrent Design Facility, in the last days, where ESA and ESA experts are preparing the future missions, where the experts are conceptualizing future missions, but those experts also have certain areas where we just have to take assumptions. So we don't really know in all areas how mature certain systems are, certain areas of hardware, where there are technology gaps. And specifically interesting for us from the operations side is how far are we with operations there? What are the constraints? How will this really be, when putting the mission together, how will this really be operated? And in order to address this, ESA has already more than 10 years ago started some sort of very extended analog campaign called METRON program. And in the METRON, we have released a lot of papers that you can find online, which were end-to-end simulations or end-to-end analog activities. So end-to-end means we went beyond normal analogs where you have a certain an asset, for example, in a lunar analog, but we tried to bring in a whole team that would really be conducting a mission, a full mission in the future. So this includes not only the engineers for the robots, but there's mission control, there is engineers in the back room, there's scientists that are coordinating, and with those teams, we are really running how you would run a lunar mission. So you see in the timeline, we had roughly every year, every 2 years, experiments also with astronauts on the ISS to simulate how it would be to have crew around, for example, a lunar orbit, controlling assets on the surface. And at the beginning, it was mostly about setting up networks and setting up the infrastructure, but most recently in the experiments that we are doing now, we are really taking a time window of, say, 1 week of operations in maybe a lunar mission. Our flight control teams get the tasks of what they need to do to achieve the science objectives. They are coordinate with scientists how to arrange it, how to prepare the trainings, the execution of the operations, and then they run through the whole process. Me as a data systems manager here, we are of course into what systems do they need, what are the systems that are required for these teams to perform these sort of operations. And here I have a quick snapshot of some of the key areas. Each of them could probably be its own presentation, but this is just as a short highlight. So what we've found is that we really want to focus in future systems also into service-based distributed monitoring and control architectures. Especially in exploration architectures, we have more and more distributed actors. So we have entities, if it's agencies or industry, that are responsible for maybe a rover. Somebody else might be responsible for a lander. Then we have orbiters. We might have relay spacecraft. We have a ground segment. We have mission control, and so forth. So there's many different elements that would like to communicate with each other. We got requests from industry that they would really like to see what is happening on assets that they're not directly controlling, like what is happening on the relay spacecraft or what is happening on other items. So to give possibilities to freely have this exchange of information between all the actors is one of the areas that we investigate. The second one is closely related. This is for end-to-end simulation infrastructure. Again, often we see that, for example, robot manufacturers, they have very good robotic simulators, but in order to really test a full, like an egress scenario where everybody can see the whole element like communication windows and orbiting dynamics, in an end-to-end scenario, we would need the capabilities to interconnect those different simulation infrastructures that are available. So there are standards for this, and we are validating these standards to interconnect everyone. And then new systems, of course, always are a possibility to spin in new technologies, to try new technologies. So we are investigating about augmented and virtual reality, mostly for us in planning or simulation. Space internet, there's a whole next generation protocol stack, the CCSTS, which for us is the standardization body, has designed protocols to be used for these sort of missions. There's also a Lunar communication standard, ESIC standard, that defines space internet, as it can be called, but it's a bundle protocol or delayed networking as one possible protocol for lunar missions. And so we are trying these in our experiments as well, how they behave and what the recommendations are from these. And then the area of artificial intelligence, where we are bringing from our standard spacecraft operations the knowledge into these other areas. Just to quickly highlight, this is an example of the virtual or distributed multi-asset operations. So we have different actors, and what we try to achieve through the standardized interfaces that are available, and that basically the different control centers can easily publish, subscribe to telemetry, that you can say, okay, these centers or these other actors shall be allowed to see this form of telemetry or information about my mission, and this then can freely be shared as a multicasting of information to achieve basically virtual distributed archives. For augmented and virtual reality, we have several projects in that area. Mostly we use it for asset and terrain visualization at the moment. So we have high fidelity simulators, but we're using the engines, for the game engines for virtual reality, to inject, for example, drone footage of analog sites, so that we can perform, that we can push the images from the 3D environment together with the telemetry from the simulators to the mission control systems, where the loop is closed, and the operators using the mission control systems can command an asset, getting the images from the mission control, from the virtual reality, as if they would be controlling the real asset. And we have used this for testing systems, but also now in the pandemic, when nobody could travel, we could use these mechanisms to still continue with certain activities just using virtual reality. And last, artificial intelligence. We have a lot of experience there from the traditional spacecraft operations, where we use it for anomaly prediction, warning systems, data analysis. So this knowledge we transfer, but there's also specific domains. For example, this is an example of a master thesis we had in our area for vision-based feature detection. So here on live video feeds of the rover, the rocks would be detected and then highlighted to the operators who are driving this rover in real time. So to conclude, to us, these full end-to-end mission scenarios are really an excellent tool and also a must to validate the assumptions that we have. We have been very active in this, trying to transfer the knowledge that we have, spinning in new concepts that are happening in industry and in commercial actors, and then trying to spin out the knowledge. So after we validate technologies, we improve the standards, we improve the software. Software that we have is to be, as far as possible, released under community license to ESA member states. So industry can use it, and we are here to de-risk the industrial investments. We are here to help, and we are here to offer services to industry. So we are looking forward to do this together. So yeah, if there are any questions on this concludes my presentation. Get in touch if you want to know more. If you want to see more operations-related topics, let us know. Then we try to come again in the future years. And thank you very much.
Thank you so much. Thank you, Sebastian. It was a very clear talk in exactly the right amount of time. We don't have any questions online that I've seen so far, and we're going to move on, but you know exactly how to get in touch with Sebastian. Thank you so much. As far as I'm aware, we still don't have Achim connected, that is. He's online, but not You have him? I'm just checking one more time. Do we have Achim?
Hello, can you hear me?
Oh, gosh. Hello. Is that Achim?
Yes, this is me.
Hello.
I'm sorry, I'm having connection problems, so I can hear you, but I cannot see anything, so I may have to deliver this presentation in the blind.
Yes, yes, and you're live to everybody here right now. It's lovely to have you. Could we see you? Is it possible to see you as well?
Sorry, it's not, at the moment it doesn't really work.
It's not possible to see you. Can you see your own presentation?
No.
Okay.
Could you bring it up for me and manage the slides?
Yes, we can do all of that if you can just say the word next, all of that will happen. So Achim Seidel from Airbus Defence and Space, you're going to talk to us about the metals factory on the moon.
Yeah, thanks a lot for giving me the opportunity to present our work. My name is Achim Seidel from Airbus. I will introduce the concept of MEFAM, the metals factory on the moon, on behalf of the MEFAM consortium. So please bring up the titles page. In this conference, in the last couple of days, we have heard a lot about elements of ISRU, technologies, process steps, infrastructure. MEFAM is an attempt to put it all together in a system approach and to find out what we can realistically do on the moon given the constraints of the lunar economy. In this work, we are focusing on metal ISRU because metals and oxygen can be produced together and will both be in high demand. Next slide, please. So we are a large international collaboration from Europe and the US with complementary expertise covering the entire process chain. There have been some presentations by other team members at this conference on other topics as shown here in orange. Next slide, please. So this is our starting point. I mean, you all know the global exploration roadmap, and when we consider that, we find that there are three really important issues that we want to focus on. Two of them are shown on this slide. We have to expect that the capability build-up on the moon will be incremental, and this applies both to the quantities that we can produce and deliver on the moon, but also, and this applies in particular to the metals, in terms of the product quality. So we will not have the perfect stainless steel on day one, but this is something that will evolve over time. And the third important point in this context is shown on the next slide, please. This is related to viability. I mean, why are we talking about ISRU? It's all about transportation costs that we want to save. And this means that any equipment that we put on the moon has to produce more in terms of output than its initial mass. This is the left picture. Otherwise, we might as well ship the products from Earth. And then the second point during the operation of the equipment, and this is probably the harder requirement, the amount of products that are produced must be much, much higher than the need for consumables or spare parts that need to be transported from Earth. Otherwise, we will never reach, let's say, a viable solution. And in order to address that, we need a systems approach, cover the end-to-end process chain from raw material to finished products. This needs to be driven by viability requirements at each step of the chain and also each development step in order to minimize or avoid the need for consumables. We need to simplify wherever possible. Not everything that is feasible on Earth will make sense on the moon. We will need to exploit synergies, reconcile desired product properties and capabilities at each step to arrive at a feasible roadmap. Next slide, please. And this is exactly our approach. This is what we are doing. We have adopted a system approach covering the end-to-end value chain from raw regolith to finished products in a large interdisciplinary team where different team members have expertise in different subject matter areas. We are looking at complementary technologies at every step. Again, we are covering the entire chain from the raw regolith to oxygen and lunar metal products, including additive manufacturing on the moon and in-space manufacturing from lunar materials. Next slide, please. And this shows you just a very few, let's say, examples of the technologies that we are looking at different stages of the process chain, sensor-based mining, molten salt electrolysis, ionic liquids for reduction, and many, many more. On the next slide, I would like to come back to the issue of capability evolution versus requirements. We can look at this process chain from two different directions if you want. We can go from left to right, from process to product. That will answer the question, what can we do in terms of what can we deliver at what quality, constrained by the, let's say, the viability constraints. And then on the other hand, we can look at the process chain in the other direction from right to left. And that will give us an answer to the question, what is needed for the intended use case? What are the requirements for the technologies and the equipment that on the moon that they have to meet in order to produce the products that the users will need? And obviously, the answers to those two questions will not be the same. And this is why it's so important to reconcile both views to find out what is realistic under the constraints of the viability requirements and make sense. Next slide. This is already the last one. The summary is that it is essential to start with the right technologies. They need to enable small, compact, and low-mass solutions, minimize or avoid the need for consumables. And one element that we see in many cases is the need for fluids, for water and process gases. That is something that we would like to eliminate as much as possible, because that again will have a very positive effect on complexity and mass of the equipment. And once we have done the initial technology selection, we will go through the usual steps of lab testing, lunar systems design, taking into account capability versus viability, synergies between the steps, and an optimization of the entire chain, of the entire system, to arrive at a viable lunar production capabilities roadmap. And that concludes my presentation. Thank you.
Thank you. We have one question for you coming from Alexandre.
Thank you, Achim, for your presentation. So you showed all the consortium and all the, let's say, the value chain you are working on. Are you already covering the whole value chain, or is there like, have you identified like elements where you need some extra expertise, or you think where you are not yet covered?
Well, this work will never be complete. I mean, we cover the entire value chain in the sense that we have, let's say, allocated or identified technologies and allocated teams working on the different topics. But there's always more that you can do. I mean, we could, for example, combine the production of metals with the recycling, because there will again be some synergies. The early stages of the process chain will be different, since we will not reduce regenerative, but process, let's say, used materials. But the later stages, like metal refinement and 3D printing, may be the same. So this is something that I think we have a very good set of process steps and also partners in the team to start this. But this is, in principle, an open architecture, like let's say, the use cases on the moon are limitless.
Thank you, Achim.
Thank you, Achim, and we're so glad that we could join with you in the end. And I'm hoping that our next online guest is with us. I believe he is. Martin Chaillet, can you hear us?
Yes, I can. Can you hear me?
Yes, we can. So you are with Space Mining Technologies, and you're going to talk about a feasibility study of a multi-purpose vehicle for commodity transportation to lunar settlements.
Yes, exactly. Good morning. Good afternoon, sorry, everyone. I'm Martin Chaillet, System Engineer at Space Mining Technologies. And our project involves many activities on the surface of the moon. But here I will focus only on the transportation part and the feasibility study of logistic rover I've been working on, called the MPCV. Its function is to transport autonomously water, hydrogen, and oxygen. And if you go to the next slide. The first step has been to identify potential customers. So as you might have heard recently, the lunar South Pole will be really crowded in the 2030s. And we identified Shackleton Crater and Connecting Ridge as the main area of our operations. Here you can see an illumination map from Lunar Reconnaissance Orbiter. And indeed, like many initiatives, private or public, are planned in this region. And that's why the research I've been doing is to build the mission and system requirements derived from this stakeholder analysis. Next slide, please. So as you can see here, refueling a spacecraft requires the most commodities, and we have been sizing the MPCV for this most demanding stakeholder. From the plan stated and their timeline, we need to be ready to have a peak demand in around 2035. And the questions are, what mass can be effectively transported, at what speed, and how much power do we need? Next slide. So to summarize the study, the results are that we need to deliver oxygen, hydrogen, and water within 2 lunar days from mining sites to lunar habitats or ascent-descent vehicles. And these performances that you can see are corresponding to be able to go to Mars from the moon. And the moon will act really as a refueling station. And the study shows that 6 MPCVs, as we designed them, are needed. Next slide. More in details, on the right side, you can see the first design we have and the key characteristics. So the MPCV is actually 100 times faster than Perseverance, around 14 kilometers per hour. And the slope capability needs to be comparable to the Apollo lunar roving vehicle, that is 25 degrees. Next slide. The concept of operation that we have designed is here with 2 paths, ideally to avoid the risk of collision and to ease the navigation. Next. Also, more information here, mainly to show that we have been assuming that the transfer of the commodities and the docking system will be in place when we will be, the MPCV will be in operation. And yeah, that's part of our assumptions. Next slide, please. So from all of this, several challenges are appearing. And the first one is the high speed, as you can see. And it implies a high power demand. And next. The autonomous capability as well implies high GNC capabilities. And these 2 challenges have been overcome with a solution. Next slide, please. That is the pass clearance vehicle. It is a similar vehicle that will prepare the terrain and make it traversable easier. And we called it the pass clearance vehicle. However, I will only focus on the transportation part and the MPCV here. Next slide. 2 other main challenges have been overcome. The thermal system has to be really sophisticated because 2 lunar days implies that the MPCV should spend a night, lunar night, that is really rough in operation. And also, we have quite a limited embedded payload available. So we assume that ISRU and storage plants are needed and that will be in place. Also, next slide, please. Also, we have been designing the concept of communication that you can see here. And we assume that the ESA Moonlight constellation will be in place so that we don't really need a direct Earth MPCV link. And this satellite will act like a lunar network so that if MPCVs are not in field of view, they can still communicate with each other through these satellites. And the range of communication that we have determined is 5 kilometers on the surface. Next slide. Eventually, the mass budget, the payload is corresponding to the commodities for us. And the total mass is a little bit above 3.7 tons, mainly due to locomotion and payload, which is well in line with the concept of a logistic roving vehicle. Next slide. From our study, we know that it is feasible with a fleet of 6 MPCV and a pass clearance vehicle to meet all the requirements we stated. And also, we have been already working on the pass clearance vehicle. And I will present later this year its feasibility study. In terms of what needs to be done, more iteration on critical subsystems that are power and locomotion are in the agenda for later this year as well. Next slide. Here you can find all of my references, and I conclude here the presentation. So we have time for some questions, and I will be happy to answer any of them. Next slide. Thank you very much, and I wish you a good day.
Thank you, Martin, for the talk, and obviously all of the people here present can get in touch with you through those means and online as well. We're going to push on. Next talk is on site. It's Matt Cross, Mission Control Space Services, with the talk entitled Enabling Autonomous Surface Prospecting and Mining with Lunar Rovers. Thank you.
Hi, and so thank you, Lisa, for the introduction, and good afternoon. So I am Matt Cross, and I'm a systems engineer at Mission Control Space Services. This has been an interesting week so far, learning about all these different plans for prospecting and mining on the lunar surface. And so today I want to talk to you about how we can improve the autonomy of mining and resource prospecting with Mission Control. So Mission Control empowers explorers by innovating to make advanced software viable for use in space. Mission Control is a fast-growing company located in Ottawa, Canada, founded in 2015. We have a world-class indoor lunar analog testbed in which we operate our rovers and robotic platforms from our Mission Operations Center. We're a young and dynamic and diverse, tight-knit team passionate about space and science and technology, and we're very keen and committed to sharing that passion and inspiring the next generation of explorers. So when thinking about lunar exploration and lunar prospecting and lunar mining, we're mostly in our view, we're mostly thinking about autonomous rovers that will be performing those activities. And so, thinking about what must a rover do in order to operate autonomously on the moon. So first off, it must be able to perceive its environment, and so it needs to understand the context of where it is on the surface and what is surrounding its location in terms of potential resources. It must understand its own limits to then operate within that environment in terms of being able to safely navigate and traverse. And then it must also be able to make its own decisions when it comes to identifying where to go next and then reaching those locations. And so Mission Control's terrain classification, novelty detection, mapping and data aggregation technologies enable this ability for rovers to perceive its environment. Mission Control's hazard modeling and prediction and traverse energy modeling and prediction enables rovers to be able to safely operate within its environment by understanding its limits to avoid any unsafe activities. And then Mission Control's path planning and following, autonomous instrument targeting, and data downlink prioritization technologies enable rovers to then make its own decisions and better operate on its own within these environments. So we're very excited and proud to be supporting the Emirates Lunar Mission, which will be launching later this year. We have an AI-based terrain classification, which will be the first demonstration of deep learning technology in a lunar mission. And our AI will help the mission science operations team to make better decisions within mission operations. And our terrain classifier is embedded on a high-performance spaceflight qualified computer and is powered by our deep learning accelerator product. We'll also be providing advanced rover navigation tools so that the science team can better understand how and where to send the rover and make suggestions on where the next actions can take place. Our cloud-based mission operations platform will enable the science team members to easily retrieve and visualize data from the mission. And we're enabling science team members and both scientists and engineers to make novel contributions to the area of lunar exploration. And so I certainly encourage everyone to follow the Emirates Lunar Mission when it launches later this year. So our AI-based terrain classification enables autonomous perception. And so when we think about autonomous perception in the context of a lunar rover, when we're looking at imagery from, say, the navigation camera from a rover, you or I or any other operators can readily identify that these are rocks and boulders. This is the regolith. But from the rover perspective, a boulder is, this means a potential resource. Regolith means a potential safe path to traverse. And a crater is a potential source of permanently shadowed regions, which could be cold trap bearing for water ice potential. And so these are what we're meaning for in terms of autonomous perception through terrain classification. And this will be demonstrated during the Emirates Lunar Mission. And so piecing it together in terms of overall lunar operations, when the rover takes an image with its navigation camera, that image then gets put through the terrain classifier, which then identifies different features and geologic features within the scene, and also potential novelties. And so in the context of lunar exploration or resource prospecting, anomalies may also indicate like unique science opportunities or unique resource potential. And all these different data products can then be aggregated onto a map to provide context and scale, which can also then enable operators to better operate within the environment, or can allow the lunar rover itself to better autonomously operate within its environment. So we're also very excited and proud to have participated in the Space Resources Challenge in this past November. And we're very excited to have been selected as one of the 5 teams that will carry on into the second round and compete later this year. So we used our cloud-based mission operations software to remotely operate our rover system within the challenge, and we were very successful at doing that. We have our own indoor moon-yard facility in which we're able to practice and demonstrate our operations software so that we were able to or be very confident in our ability to perform similar operations. And so I have colleagues online, so KZ and Veronica will be available in the virtual lobby. And if you are interested in test driving our rover in our moon yard, I invite you to, starting now and during the coffee break, go visit them and take our rover for a spin. And so, simply, we want to simplify lunar exploration, and so we want to know how we can support your next mission. So thank you very much.
Thank you. I will have one question for you. So when it comes to AI or machine learning, I guess it takes a lot of resources, like computer resources. Can you do that directly with space hardware on a rover, or would you have to stream back the images and do the processing of the data on Earth and send back the command? Or?
So the training of the like AI and machine learning models, that in itself is fairly resource intensive, and so that is done on the ground. But the actual model we will have running on spaceflight computing technology.
Okay, thanks.
There are a couple more questions online for you, which I'd love to ask you, but for purposes of time in the next coffee break, I'm afraid I'm not, but it's very, very interesting. Thank you so much, thank you, and we do wish you well with the Emirates challenge ahead. I was actually thinking about the Emirates because there's a lot of sand over there and you could make another lunar base over there. Anyway, on to our next talk. It's from Gradel. It's Farzana Golami, who's going to talk about robotic filament winding lightweight technology for sustainable space exploration.
Hello, good afternoon.
I'm really delighted to be here today and to present you on behalf of my colleagues in the Space Department and the Lightweight Department of Grado.
Rosanna, could you go closer to the microphone so everybody can hear?
Sure.
Thank you.
Lightweight technology for sustainable space exploration. So, in our journey to explore the universe, it's necessary to overcome the multiple challenges. And in Grado, we believe that we can be part of the solution to in-space manufacturing by our lightweight technology, and by making it a step forward toward reality. So GRAM is Grado Robotic Additive Manufacturing. So in this the video, it's basically the process is putting the endless filaments in the right direction in a way that can build very strong and very light structure. So the process is totally digital, and the structures can bear the maximum loads using the minimum materials. We can use a set of different materials, let's say carbon fibers, basalt fibers, glass fibers, and at the end, we can achieve up to 70% waste saving. We can see, so for example, here is like rayon fibers and different kind of structures, as you can imagine, in 3D space can be built. So our process is a step change in manufacturing because it's very light, it's very strong, and the process is relatively fast. So you might want to know how much light and how much strong. So imagine this structure that I already brought into the scene. So it's less than 200 gram mass, and it can bear more than 1,000 kilogram tensile forces. And in terms of compression forces, another design is around 230 gram mass, which can bear more than 1 kilonewton force. So in this sense, it's like, it's the smart way of using the material, putting the materials where necessary. So why lightweight is important, especially for space and also for the Earth? The first advantage comes back to the material. So basically for the Earth applications, we can use bio-based materials. They can be recycled. They can be, they are renewable materials and can come back to the Earth. And in terms of using the products on the moon, we can use also the basalt, which already exists on the moon. So it's about utilizing in-situ resources, either on the Earth or during the mission. The next is because we are using the minimum material is resource efficient, and the manufacturing process is zero waste. And finally, because the structure is light, during transportation and launch, we are consuming less energy, which is making it energy efficient. And on the moon, on the other side, it's being lighter, it means more capacity for payload. Or it would mean less energy consumption during the mobility, and which can lead to smaller size of the power subsystem and also decreasing size of mobility subsystem, and it can also would mean extended lifetime of the battery. So to put all of these scenarios into one example, I chose the scenario-based approach. So the NASA has already provided some architectures for oxygen and water production on the lunar surface. So one of these scenarios is mobile water extraction, which is basically the rover goes through different parts of the moon. It collects regolith and directly produce water. So in this example, the rover mass is about 7,000 kilograms. Which has also a very big power subsystem. So I imagine that, okay, if we use the GRAM technology into this architecture, what would be the effect of this change? So, yeah, as I already told, that the potential for mass reduction is about 70%, but yeah, it's in average. If we imagine that we can decrease the structure mass by 40%, it means already the structure would be 1,000 kilogram lighter. But it's not only this, it's also the mobility in energy consumption based on the Apollo mission that was the only mission that was sent to the moon. The energy consumption during mobility is about 3.5 joule per meter per kilogram. And if we imagine that each time the rover goes through a distance of 30 kilometers and with a speed of 5 meters per kilogram, the mobility energy would be 100 megajoule less. So considering the specific energy and the specific power of the batteries and solar panels, it means that the power subsystem would be 10% lighter. And it's not only this, but it can also affect the thermal subsystem and lots of other subsystems in the rover. So it can lead to a very high mass reduction in total. So based on the theme of this space resources, we can answer also how to make it sustainable. So the first aspect is using the regolith in space products. So the University of Aachen has already used the regolith stimulants to produce fibers using the external solar systems and thermal regulations. And knowing that it's already would be feasible to have access to lunar regolith as fibers, we can set automatic robots and produce structures on the moon. With this, I end my presentation, and thank you for your attention.
Thank you, Prasanna. We have a question from Aidan.
Just a quick one from myself. Thank you for the very innovative talk. You're approaching your process is quite different from traditional design approaches. How do you actually go about realizing these designs using software or modeling? How would we approach using this approach? You know?
Yeah, it's actually it's had lots of engineering behind. So the process itself would be fast, but the engineering is the most important part, because it's important to know exactly what are the load cases, what are the atmosphere, which kind of material would be the most appropriate, and based on that, we need to design. And the designing the mechanical part and also programming the robotic path to wind is also another aspect.
Okay, thank you.
Contact us. We would be happy if you have some structures you would like to make lighter. We can realize that.
Thank you so much. Thank you. Thank you, Prasanna. Our next talk is by Leonardo Turchi from ESA, and I believe we have somebody joining him online as well, a colleague. A talk with a long title. It's the Electronic Fieldbook Tool Suite, Field Science and Prospecting Decision Support Tools for Structured Information Collection and Distribution for Astronaut Training and Human Planetary Exploration. And you're reminding me, because you did 2 poster presentations, doubling your chances of winning. I've been told that there are 3 posters almost neck and neck, so get your votes in, because I think we'll probably close voting after the next coffee break. So 3 posters, I don't know if it's yours or not, are neck and neck, so another opportunity to just say, do vote.
Thank you. So glad to be here. Good afternoon. I'm Leonardo Turchi. I work for ESA in the development and field utilization of a suite of hardware and software tools for supporting the astronaut training campaigns of the European Astronaut Center. I will introduce you to the Electronic Fieldbook Tool Suite. So the suite has been developed and tested in the framework of the CAVES and Pangea astronaut field training programs in support of geological planetary surface operations. It is composed of several projects, and each of those communicates each other through the electronic field book. The main objective of these tools is to provide situational awareness and decision support during field science operations. The EFB is a platform that, the main objective to provide communication and so data collection and distribution from the crew operating in the field and the scientists in the ground. Connected to the EFB, there are a number of instruments and sensors, including handheld spectrometers, providing mineralogical and chemical signatures for the identification of relevant samples, mineralogical databases, a machine learning algorithm for autonomous classification of these minerals, panoramic cameras, and optical imaging tools, providing contextualization of collected samples and overall situational awareness to scientists in the ground. The focus of the presentation will be on the parts highlighted in red, although the suite is based on a modular approach that can embrace additional tools and devices. So the EFB platform provides the ability to plan and execute traverses using custom multispectral 2D and 3D maps, provide data integration and harmonization in support of contextualization of data during operations, information synchronization amongst all the mission elements with automatic merging, and this is also possible through a field deployable network that is tolerant to network disconnections. In addition, DFB provides easy access to reference and easy data interaction through ad hoc views made on, depending on the mission role. And finally, also access to reference and creation of reports. The main goal of DFB is to provide the science decision support, contextualization of sample collection, and situational awareness to the whole mission team. And DFB has been used in ESA Pangea campaigns since 2018. Here we see some advanced modules of the DFB tool suite, in particular a machine learning algorithm to help identify minerals and a series of databases to help select the best geological samples. So now, astronauts are not usually expert mineralogists, so a system, an information system, could provide support to them in the selection of the best sample. Using portable spectrometers, users can record a spectrum of a mineral out of a sample, and our system then uses machine learning software to identify this mineral against a mineralogical database, which contains also a spectral archive that stores more than 10,000 spectra of minerals and rocks. Now, there are mainly two types of data that we can use. Molecular spectroscopy, Raman and VNIR, providing the information about the structure of the mineral, and atomic spectroscopy, LIBS and XRF, providing the elemental composition. Combining the two methods provides complementary information about a mineral, and combining inputs from multiple spectrometers can increase overall accuracy. Our method achieves 85% in accuracy in the identification using only one input, whilst combining inputs from two different instruments would increase the accuracy to 92%. Now, the mineralogical database, in the mineralogical database, we also store detailed information on all known minerals that are detected on the Moon, Mars, and asteroids. And for each mineral, we characterize in the database basically the chemical formula, the elemental composition, the physical properties, and the scientific significance. This information is then provided to the users in addition to the mineral name in order to facilitate decision support. The quality of the database is very high, and it's also kept synchronized with the constantly updated versions of the International Mineralogical Association's IMA catalogs. For each mineral, it's given a description of the formation environment and as well as the relevance and presence in similar terrestrial analog environments where also Pangea expeditions are conducted. In this way, the mineralogical database helps to interpret the importance of each mineral and therefore facilitating sample collection. So the EFB tool suite, together with integrated advanced modules and with all the instruments, has become a key component of the ESA Pangea campaigns. And here you see the setup, for example, for ESA Pangea X 2018, with a simulation, a crew simulation with 2 crew members in the field. Following the successful outcome of the supporting astronaut campaigns, ESA is now preparing industrial activities for further development of the EFB as potential contribution to the Artemis geological surface operations. We think it is a good opportunity for Europe to have this instrument developed in time for the next challenge of human exploration, together with the knowledge on how to conduct meaningful science operations and then supported by a host of new software and hardware tools. I'll be here for questions. Thank you.
Thank you so much, Leonardo. We have to move on because of time, but I know people know how to catch you and your posters outside. Thank you very much. Thank you. Final talk before coffee break is Maciej Józefowicz. I am sorry. When I see all of those consonants together, I know I've already got it wrong. Can you hear me?
Yes, I can hear you. And you did a good job. Thank you.
Oh, thank you very much. You're from the European Space Foundation, and your talk is entitled Applicability of Mirrorosphere Spectrometer for Detection of Lunar Sulfides and Oxides.
Exactly. Thank you for the introduction, and I feel like I'm competing with coffee, so I will be not keeping you very long here. I will tell a few words about the consortium in the beginning. So we are a consortium of 4 organizations from Poland, and 2 of them are institutes of Polish Academy of Sciences, which is Geological Institute and Space Research Center. Myself, I represent European Space Foundation, and we are responsible for business development, and we have also a commercial partner on board, SKA Polska, who provides the commercial drive for this project. It's a project with scientific roots, but it is heading towards commercialization of space resources. And I'm also happy to tell that half of the team listed here are geologists, so they would really be interested in the previous presentations. We hope we can get some interface with the platform. But we are developing an instrument, an orbital instrument, which is a spectrometer. It's a far infrared spectrometer operating in 21 to 30 micrometer range, and it is dedicated especially for detection of ores, mineral ores, oxides, and sulfides, because specific ores from those groups show very good spectral features in the selected range, while other space resources do not necessarily show this. So we focus on those 2 groups. And we are not detecting specific elements. We are detecting minerals and mineral markers and correlating appearance of specific ores with our internal database, which is not automated, but it's a vast knowledge of our geological team. We are yes. Next slide, please. Okay, thank you very much. We are focusing on oxides on one side, and if we are talking about oxides, one have to mention ilmenite, which seems to be one of the most promising targets for mining on the moon, because it contains not only the metals, iron and titanium, but it contains most of all oxygen, and there are already processes designed to extract this element from this mineral. We know that ilmenite is abundant. We also know that specific concentrations appear in specific places of the moon, which are exactly the Maria, the places of ancient impacts. So this is where we want to look for the ilmenite and other oxides, but we want to do it with a more detail than it was done before, because the previous data are from older missions such as Clementine. We are going to provide a service with much higher resolution, much higher detail. Ilmenite is also interesting because it actually absorbs the helium-3 from the solar wind. So this proves to be a really almost a holy grail of space mining on the moon. On the other hand, we are detecting also sulfides, and troilite is one of the most abundant sulfide ores. It's an iron ore. It's one of the most abundant on the moon. Pyrite, on the other hand, which is very close to troilite, can also be present because it is present in the asteroids and in the meteors. So by correlation, it should be present in impacts. And we are hoping to detect pyrite as well. I will tell a bit later why pyrite is very important to us. But there is a whole group of other sulfide minerals that we can detect, and they also are present in the Maria, because the Maria cover actually the map of the iron, spectrometric map of the iron. So by correlation, this is where we going to look for the bigger concentration. By correlation, we are also able to detect other elements, so chromium, vanadium, copper, nickel, platinum group elements. Not all of them appear on the moon, but the device is capable of detecting them all, either directly or by correlation with the mineral appearances. So the device is capable also of being used on not only on the moon, but also, let's say, on asteroids or on Mars, where we know that those elements can be found. Commercialization is very important, and use cases are very important for us. We are not doing this only for science. We are doing this for science, but also for development of the commercial sector. So we've identified our two leading cases for interest in our maps that we will be delivering. So if we are speaking about ilmenite, ESA is already funding a demonstrator of an ilmenite processing unit, which will be extracting oxygen from the ilmenite. So this is a part of the value chain that is already being established. So first you have to really find the optimum concentration if you want to really land on the moon, and you have only one chance to choose your spot. You want to land in the optimal place. So we will be providing those data. And another case is pyrite, and actually there was a presentation earlier this day from Tavi Radik from the Italian University of Technology from Estonia. We have very interesting cooperation with this team, because this team is planning to create in situ photovoltaic panels out of pyrite crystals. So either if we find pyrite directly or troilite, we can provide information about the deposits of those sulfides that can be used for photovoltaics. So this is also a good part of an emerging value chain. Speaking of our space missions, I have to mention the volume of our device. It's not a very big device. It's about 10 kilograms. So the dimensions are 42 by 32 by 32 centimeters. So not really a CubeSat, but still it can fit in other missions as not as a main payload, but as one of the payloads, or can be replicated as a main payloads or the smaller satellites, while the industry is already running full speed. I've mentioned the minerals that could be detected on the asteroids. or on Mars. Speaking of Mars, sulfides are very abundant on Mars. They are mostly related to hydrothermal and volcanic features. So they appear in specific spots, and our team is also identifying those spots, not with the device yet, but we know where to look for. Finally, there is an Earth application. Unfortunately, water obscures the spectrum in our range, so we cannot use it on the orbiter because of the water column. But we can use it on a drone, and especially in arid areas and polar areas where the water content is expected to be lower, and when the altitude is also lower. So the shrinked version of our spectrometer can be used for looking for new deposits on Earth. This is quite important. Well, the glaciers are receding, so they are exposing new areas of the rock bed. And whether we want to exploit it or not, we still have to map those areas. And also in terms of geopolitical situation, new deposits of iron ores are very interesting nowadays. Most important for us is the fact that ESA is actually appreciating our commercial attitude, and we are running this project currently under ESA Business Applications, Space Resources Enabling Study. This is a very interesting ESA grant because it actually expects us to generate a marketable service and business plan, not necessarily hardware. We have some hardware already done, but most of all, create a business model. And this is a very important step for us, but also I think for the whole community and for ESA, the change of the attitude towards offering commercial services in space mining especially, or space prospecting, is very promising. So actually our service will be based on offering the detailed maps of potential landing spots, consultation on the landing spots, and identification of minerals in selected spots. Within this project, we are following two paths. So one is a traditional market path, and another one is the innovative one, where we are actually analyzing the potential of blockchain technology in order to streamline the transfer of data, the transfer of services, and the resources, financial resources within the service. This is very promising, especially in terms of building interfaces with space resource registries that appear and that have been also presented here. So we want to create a universal way of connecting to those registries and utilize the blockchain technology as well. Thank you very much. This is, I think, all from me. I will be happy to answer any questions if you have some, and have a good break.
Thank you. Thank you so much. A really interesting talk, and I know that Danon has written a question online which you can reply on online. I think everybody here is in need of a stretch and a break, I'm afraid. So sorry there's no live questions to you, but they'll all be revved up after a little bit of coffee and sugar, I'm sure. So back here in 20 minutes, we'll start again at 40 minutes past the hour. Thank you.